please try to allocate again one GPU on cycle so we can proceed to the other examples that I have. So you can ask for more time, because if you ask for 30 minutes, after a half hour, you will need to redo it. Okay. So is there any question from what we discussed in the previous session, or we move to the next one? Okay. So yeah, up to now we have seen how to write small kernels, how we take care of synchronization for the threads and for doing atomic operations. We have seen the vector addition, the dot product. So it is something that is important when one wants to port an application from a CPU to a GPU, is to check the timing. For instance, how well the code implemented performs, and in order to do that, CUDA provides some special kind of events that allow us to do these timings. So timings exist also with CPU, but when we want to do a timing specific for parts related to GPU operations, like transferring data or execute a kernel, then the CUDA timers are much more precise. They have a resolution up to 1 microsecond, which is extremely good. So it is important to use those timers. Okay, and the situation goes like this. In order to do the timing, you need to create a CUDA event. So a CUDA event is a specialized kind of variable that is called CUDA event _t. And here I define two CUDA events, a start and a stop. Okay, this is just a definition. However, those events need to do some kind of allocation under the hook. And here one needs to call an API, a CUDA function calls CUDA event create to take care of all the necessary steps to create the event. And when the event is created, it doesn't mean it has started. It's just you allocate the memory, as I said, for example. So if you want to start recording the event, you need to call the API function CUDA event record. Okay, and you pass the variable as an argument, and then you do the operations that you want to measure, like the CUDA malloc, like CUDA memcobit. You can execute kernels, okay, in this block that you like to measure, and then you can start the stop event. Okay, so the stop event will come always after the regions that you want to measure the time, and you need to synchronize now the events. So synchronize means that wait there. It tells to the host to wait there until the events that are proceed are completed. And if you have the start and the stop event, then you can call the function CUDA event elapsed time, provide a variable, a float, for example, to get the time in a single or double precision, and then provide the two events. And this just calculates the time, and this is given in microseconds, okay? Sorry, milliseconds. And then you destroy the two events. Okay, this is important to destroy them, otherwise you may don't free the memory that allocated with the creation of the event. Okay, let's go to see the example that I have prepared for the timing. Okay, so it's the example of adding two vectors that we have seen before. However, here I have the two events that I stop. I put my record before I'm doing the malloc. Okay, and copy the data, add the vectors, copying back the solution, and up to that I finish with my operations that I want to measure, and measure the time. Okay, we can run, for example, to see what is happening. Okay, so this tells you the elapsed time. It's in milliseconds. This is about 0.5 seconds, and the last element just for make sure that everything is okay. Okay, so one thing that I haven't mentioned before is that what is the meaning of this argument that I passed here. Okay, so this takes me to the point of what are CUDA streams. So you can imagine that this CUDA stream is a stream, okay, a fictional stream, that on this stream you can put stamps with events that you want to evaluate on the GPU in the specific order that you put the stamps on that stream. Okay, and this stream will allow us to do something very important that I mentioned in the beginning of the presentation, which is the overlap of computation and computation and copying of the data. Okay, so let's see now how to do that. So because the streams now, if we want to put copy of the data on those streams, in the specific case that we want to overlap the computation with the calculation, we do not want to do the copy in the synchronous blocking way we discussed before, and there are functions on the API that allow us to do what we call asynchronous copies. Okay, but in order to be able to do it asynchronously, so you do not block until the copy is finished, we need a concept that is known in computer science, which has to do with page locking. So I will try to briefly explain it so you get a taste of what is this about. So on a computer, you have the physical memory. And on this physical memory, you allocate and deallocate memory. And usually, there are gaps between allocations, because you imagine you allocate and deallocate, so during this deallocation there is a gap. But if you try to use the remaining free memory, it will not see it as a continuous buffer that you can allocate. There are only gaps. So this is why they have computer science idea that you do a virtual memory that allows you to implicitly see those gaps to be continuous and be able to use all the available memory that you actually have. However, this needs page shuffling. And if you do this page shuffling, you cannot do an asynchronous copy. It will not. It will have problem to happen. So with this CUDA host unlock, we lock the pages for that. Okay, and I will show you now how this is done, the allocation. But for every CUDA host unlock, you need to remember that we need a CUDA free host. Okay, so now in order to overlap computation and communication, we need at least 2 streams. Okay, so imagine that we want to add 2 vectors. Okay, so those 2 vectors, we can break them into chunks. Let's say that we have one vector and we split it in 10 pieces. And here we put on the stream 0 to start copying the 2 input vectors x and y to GPU for the first chunk of the vector. And then you call the kernel. That all this you put it on stream 0. And this all is done in an asynchronous manner. However, then you start on stream 1 the second chunk, and you copy x and y to GPU, and then you call a kernel, but for those elements that you copy here. So all this done asynchronously, and you asynchronously copy from the first chunk the result from the GPU back to the host. Okay, and this is the way that the stream goes. So you have already noticed that there could be pieces when one calls to do the kernel for computing the addition for the first chunk of data. And there are cases that you overlap with copying the data from the second chunk. So in cases like this, you can overlap the kernel operation with copying the data. Okay, so, and this is very important because if you do not have feature like this, you cannot make scalable codes. And this is something that I will explain now with an example how we can do that. So I have it also here. I think should be this one. Okay, so let's go through this to understand the details. So we have now a big vector. So these are the order of 100 millions, the size of the vector. So I make them a big now so you can see the improvement. And I say that I want a chunk size of about 1 million. So this, let's say we have about 100 chunks here. Not about 100 chunks. And this is our main function. And we will need, because now, as I said, we need 2 streams, I need 2 different sets of device pointer. And this is why I put an index 0 to remember which I use for stream 0 and stream 1. Okay, so this is to do the timings. This is, I explained it a few minutes ago. And then we need this special type of variable, which is a CUDA stream. And I create with the API function 2 streams, the stream 0 and stream 1. And I allocate memory of chunk size for my input and output vectors for the 2 streams. And now we said that if we want to do this overlap of communication and computation, we need to have page lock. And this is what is done here, CUDA host malloc that I have described. And this is page lock. This is allocated on the host, but it's page locked. And yeah, then default flags are given here. And then you can initialize your vectors, whatever. But this is the most important piece that we need to do. So this piece that I show here in this for loop is actually what I explain here with these boxes. So let's go again and have a look. So since I have two streams, I jump every two junks. So this will do then junk 0, for example, and this you will do junk 1. This will do junk 2, and this junk 3. Okay, etc. And I'm starting doing asynchronous copy. So this is why here I call the CUDA main copy and the asynchronous version of it has this unseen. So these are the same, are the standard way that we're doing it. And the additional flag here, it says where in which stream to put this kind of operation. So I put in stream 0, I copy from host to the device, and then I call the add kernel, specifying which stream this kernel will be on. Okay, and then I copy back the data. So all this goes to stream 0. And then on the next one, I put them on stream 1. Okay, this is exactly the same. However, I access data I plus junk side. So to take me one junk size further. And I do this all for loops. So I put my events on these streams that I want. However, this is all asynchronous in the sense that probably none of them have completed until I reach this point. And I'm saying that now I want to synchronize myself with both streams. Okay, so I wait here, the host wait here until those operations are all completed. But events like what I discussed before, this one will happen here. And we will overlap communication and computation. And then when the streams are synchronized with the host, I compute the time, and then I free memory. Okay, so always remember, CUDA host alloc goes with CUDA free host. CUDA malloc goes with CUDA free. And you have to destroy your streams. And yeah, let's run this example. So before this, I have this add vector just with timing without any improvement. So it is interesting now to see how much this has improved. Yeah, you see this is the same number of elements that I will put now. This is about 100 million. This was just the timing without an improvement that I discussed now with computation and the copying data overlap. So before it took about 0.5 seconds. Now let's see how this will perform when we do this overlap. Okay, now it needs much less. It needs 88 milliseconds, which shows how important it is to use such feature if one wants to make codes faster. So do we have any question about the concept of CUDA stream? Because it's not so trivial. It's an advanced feature, so it's yes.
Could you please show it to us on the big image? Because I understand like how it runs, but if you show us like on the first image that you
this image.
No, you had like the image where you show the blocks and the threads, and there was like a big image at the beginning.
Yes, this many slides before.
So
yes,
that thing that has the whole image of CUDA that will help like give us a clearer image of where that one.
Yes.
So where do streams comes in this feature?
Okay, the streams are beyond the threads and the blocks. Okay, the streams, it's not any physical thing that you can find on the GPUs. It's convenient from the point of view of programming that allows to the GPU to know the order that execute commands like copy, commands like kernels. Okay.
Okay.
So it's beyond that picture.
Okay.
And the interesting thing is that you can put more stream, not just one stream. The default stream is 0, is the one that I show in here, exactly here. This 0 is just the default stream. However, you can put more, and the GPU can simultaneous goes to through those streams. Okay, and of course those streams and overlap in such kind of calculation and coding and calculation. It has a significant improvement, because imagine it has to wait to get all this size of data and waits there. So it's sitting idle. So you are losing time of not using it, and this is what it gives this significant improvement.
Okay, thank you.
Okay. Now, after we have seen a way to overlap computation and communication, let me go to the topic about the CUDA errors. So up to now, we haven't seen any approach how to take into account errors that might be raised during the execution of the code. For example, you may have errors out of memory, or you may have errors, probably most of you have faced segmentation faults. So how we catch those errors, and if we catch them, okay, it depends on the user and on the error, what kind of exception you have, how you can handle this error. Okay, there are two types of, two categories, let's say, of errors that one can face when works with CUDA. One error is that we have the API functions. We have the CUDA allo, we have CUDA memcopy, etc. We have seen many of them. And all those API functions actually return something. Up to now, I have ignored it for simplicity, but they actually return something. Okay, and they return something that they return is related to if they have successfully completed or not. Okay, so here what I'm trying to do, I will try to explain it, is just to create a wrapper to easily make use of these checks. So in this wrapper, this is just a macro, in order to be able to get the file a line that this kind of error appears. And this actually takes the CUDA error that is returned from a function, for instance, the CUDA malloc. Okay, it gets that error, and then it checks it if it's a CUDA success. A CUDA success, which means everything ran without any problem, it will proceed. Otherwise, it will printf this error. Given the error that is just, let's say, an index, this function gets a string in order to return to you to make sense of the kind of error. And for instance, if this is not success, you may exit. Okay. And I have an example here under the 5. Let's have a look. Okay, so this example, I'm trying to make this to if it can give me out of memory. So we know that this in GPUs, they have 32 gigabytes of memory. So let's, so this is in megabytes, and then this is in gigabytes, and I'm saying 32. So this is the size I'm trying to malloc here, for example. So let's try to make it 31 for a moment. Okay, and if I try to execute it, okay, it gives the invalid, I may need to make it smaller. Let's do it to, okay. Why it gives me that one now? Invalid argument. 21. Yeah. Okay, I have this one. So let me, okay. So compile it and run it. So now I don't ask for too much memory. It should finish without any problem. However, when I try to increase the memory, let's make it 50. Yeah, and let's try to compile it. So now it maybe not give me error because the compiler is smart enough to figure out that might not use it and avoid it, but here is not smart enough. So actually, when I increase the memory more than I have, you get this error. I think it's at 32. I mean, the GPU memory, you do not have available completely 32 because some of the memory is used for error corrections, about 1 gigabyte maybe. So in order to check where you get out of memory, you need to take this into account. So here I still get this out of memory. So if I put 31, now we should be okay. Okay. Okay, now it's okay. You see, after you try to allocate more than what you can have, you get this error. Okay, so it's important to have this kind of safe call. Otherwise, you may have not got it when you try to allocate, and will have problems later when you try to do calculations. Okay, so keep this in mind. Now, let's go to the second category of errors that we may have. And in this category are the errors that you can have in a kernel. Okay, so in a kernel, imagine situations that you go out of the size of an array that you have allocated. Okay, so but we know one thing that we know that we cannot do now is that the kernels are all asynchronous. Okay, and because the kernel are asynchronous, we may proceed after we call this kernel and don't be able to get this error. So I will explain now how we can check this kind of errors. So yeah, I have again a wrapper that in order to be able to pass the file line, so I can easily find the errors. Okay, and after, for example, when we have the kernel call, we can put this CUDA check error. And what it does inside this inline function, it gets the last error available. So when there is an error, the CUDA put it somewhere in a buffer, and you can pick in that error with this API function. You can get the error, and you can from the error you get the string, so you can see what kind of error you have. However, if you have the situation that I mentioned with the asynchronous kernel, you need to put a synchronization before this function is executed in order to return some kind of error. Okay, and this is you can enable if you have to enter the debug version in order to get mistakes that they have to lead in such kind of errors. Okay, so let me go to an example that I have prepared so we can understand better the situation. So let's go to the add vector example that I have shown many times, and we will try to make it to go beyond the bounds of the beyond the limits of the vectors that we have allocated. So here I just put n to be very big, n to the cube, and this is access the memory beyond the boundaries. Okay, here I do it intentionally, but when you implement something, you may do it by mistake. So if we try to execute something like this, okay, you get that in line, this is the line, okay, 72, an illegal memory access was encountered. So you go to your file, you go to line 72, yes, and this is where I have put my wrapper, and it checks that the error, so the error has happened in the kernel, where I have intentionally, in a specific case, got out of boundary. But you can have also other kind of errors, like you reach the limits of the registers that you use, or the shared memory that you try to allocate is much more than what is available. And this will give you all this information that you need in order to find solutions to the problems. Okay, so checking the errors, it's something that you need to keep in mind. Okay, so GPUs have also other interesting things that they can do. So up to now, we have seen the cases that we transfer data from the host to the device. Okay, so one may think that always the data that the GPU will process should be available on the device memory. However, this is not always the case, as we will see now. Of course, if you want to use a lot of those data, you will transfer them once on the GPU, and you have them for a lot of calculation. However, imagine situations that you just want to copy a vector and do a vector addition, where we know that vector addition, it's memory bounded, not compute bounded. So it means that it will it will not do a lot of operations per data it has. For example, the matrix multiplication, it's compute bound. It needs to do a lot of operations per data available. Okay, so in cases that I may have vector additions, you can do the following trick, okay, which is called zero copy memory. So yeah, let's go to the examples. This exists in EX6. And yeah, let's open it. Okay, here I have my wrappers for checks, and here is my addition, but let's move to the interesting part. Okay, so if we want to enable this feature, we need to call the API function, which sets the flags for the device. So here we will say to the device that we want a mapping to the host. A mapping means that it will create a unified memory with the CPU, so it will sit like it exists locally. However, under the carpet, is accessing the data. Okay, and in this case, if we want to allocate it, if we want to do this kind of zero memory copy, we need to allocate the host pointer again with the CUDA host alloc, not the standard malloc. And here in the flags, we are saying that this should be special kind of pointers that I will do a mapping of this CPU memory to be able to access on the GPU. Okay, and there is one more steps that one needs to keep in mind, that from these pointers, the host pointer, to get a device pointer. This is exactly what this function says, host and get device pointer. And you just give your host pointer as a second argument, and you get your device pointer. And now you are ready. It's like you have copied them explicitly, but we will do it without really copy them. So in situation like this, you don't need to worry that you use a lot of GPU memory and you very fast reach out of memory issues, because now it physically exists on the host, but it's copying them when it needs to process them only. Okay, so in this, yeah, and then when you call the kernel, and then you synchronize, for example, in order to get the data. This is what I do here. Okay, here I do also the timings, and then that's it, it's finished. Okay, now let's try to execute it. Okay, so this is it's the example that I showed also before, adding two vectors with about 100 million elements. If you remember, we have seen three cases. The first case that I have shown, it was a standard approach. So you do a CUDA mem copy, and then you add this kernel to do the additions. And it was getting me about 400 milliseconds. Then I have done the second case, where with overlap communication and computation. And there it was giving me about 70, 80 milliseconds. And now with that one, with the zero copy case, I'm able to get about 70 milliseconds, which shows that it was a significant overhead to copy directly the data to the device and have the GPU idle while waiting for all the data to come to call the kernel. However, here, when I do that, the data are on the CPU, and when the GPU starts, on the same time that it tries to do the computation, it calls for the data from the CPU to come. However, this has a negative side, in the sense that if you want a lot to access the data, the same data many times, then you need to transfer all the time from the CPU to the GPU implicitly. So this will give you a significant overhead. But in cases like this, that you do it once, it's really worth to use the zero memory copy. And you do not need to worry that you will go out of memory, because this is physically on the CPU, this allocation of the vector. Questions up to now? Okay, so this was not so interesting, however important for improving the performance on a GPU code. So yeah, this is something, yeah, it's worth remembering, but okay, it's not so important for now. I want to go to some more important things to discuss. So yeah, many people now do not use medium level languages like C, C++. Okay, and they prefer to use higher level languages like scripting languages such as Python, R, or Julia, etc. There are several. Okay, and one may wonder, in this case, how I port my code from a CPU only to a hybrid code that mostly using GPUs. So by the way, how many of you use Python? Can you raise your hands? Okay, I see 5 hands, which is good enough, so we can have a look on these examples. However, there are some people that they may use R, or also in R there are similar libraries exist, but I will show you here the general idea with Python. That is, I think, the most common one. Okay, so now if you want to be able to use CUDA through Python, and you have pip, you know that it allows you to install packages for Python, you can run pip install pyCUDA. Okay, and this will install pyCUDA for you. So as the name says, pyCUDA means use the CUDA library, but through Python. Okay, so in this case, I already have them. So let me show you. So if you have run this compile all, your path variable should already be set to see this path that I have my Python interpreter that has underneath the package that I have installed. However, if you want to use your own Python installation, you need to remember to install the pyCUDA if you want to use it. Okay, for example, if I use my IPython, the interactive Python, I can import Py. I should have it. Oops, pyCUDA. Okay, I have pyCUDA and I can import it. Okay, so let's exit it. And now in the CUDA API that I show you in C, we had to call functions like the CUDA memalloc, that now in pyCUDA it's just memalloc. So they just remove this CUDA and always in front of the functions. Now the CUDA memcopy goes to memcopy. However, they put an underscore here to specify the direction of the copy. So here it was only CUDA memcopy and you were providing a flag. Now it's a mem copy, and we put underscore, and then here specify the direction of the copy. Okay. Now let me open the example that I have so we can see it. So it is an example 7. It has the Python script, so we can have a look. So the CUDA that we loaded. So by the way, have you tried to check that you can also load the CUDA?
I don't have IPython on my prompt. I cannot run IPython.
But have you tried to specify the path that I use, because it will take some time to install it again. So if you do export, like I show you here, if you go to compile and do this export, you should be able to look Python.
Yeah, my mistake. I thought that it was going to be exported by running the compile, but I had to do it manually. Sorry. Yeah, it works.
Okay, so now you should be able to see it. And let's open again the script. So you import from CUDA driver CUDA, so you will be able to have direct access to the CUDA API. Okay, this is what you need, is just some initialization. And another thing which is important is that CUDA has also the compiler. So you can say CUDA.compile and do an import source module. So this will allow us to write as a string the kernels that we have implemented before. So you remember that we have implemented a kernel like this. Now we will do it through Python district, and we say that let me show you here. So we call this source module with a string that we call. I put triple quotes because I want to use many lines, and this mod has inside maybe many functions. You can put many, not just one. And you say that mod.getFunction, and you specify the name of the function. And here it compiles it. Under behind the scenes, you don't see it, but it compiles and make the object file for you, and then you can call it. Okay. So in the next line that you see here, it's like the line that we have in C with these triple quotes to call a kernel. However, here we call it like we call functions in Python. So let me also say here that we allocated memory. So here I do CUDA.memallocate. I say the bytes that I want, and this get me the device pointer, and then I memcopy from host to device. Okay, so those things here, A_GPU, B_GPU, are actually pointers that are given to the function that we compile here. And of course, what we need is our block size. And here I specify how many threads I want. I specify the same number of threads in each of the 3 directions. And we said X, Y, Z. So this is why you see 3 here. And then just make it one-dimensional with the same number of treats as the elements of the vector. And this will call the kernel. And then I do a CUDA mem copy from device to host, and I have my vector. And this is simply in Python for those that they don't want to mess with C. Okay, and then one may execute this. So Python and the script. Okay, here total difference, it means that I'm doing the addition of the vectors on the GPUs here. And here in this A plus B is done just with NumPy, because A and B are here are just NumPy vectors. So this A plus B is done on the CPU, and it compares to see that is what has been done above on the GPU. Okay, so they fully agree. So you know that this addition of the vector on the GPU is done correctly. Okay, so let's move forward. So this PyCUDA, I mean, you can use this lower level, let's say, way to use GPU arrays that I mentioned with pointers, and this was more C-like. However, if you like more Python ways, you can use from PyCUDA. There is a module which is called GPU array. Okay, and in this way, you can have commands like this. Let's say you have an NumPy array. So this NumPy array, the standard way, it has this exist on the host memory. Okay. So about Milto, you need to be on a GPU node to do that. This is why it gives you the error that it cannot find libcuda.so.
What do you mean by being on a GPU node?
Now you are on the front end, right?
Yeah.
And you need to do the salloc in order to be on a GPU node. If you are on the GPU node, you will see here, do you see my screen? It will say in GPU and the number of the GPU node it is. In my case, a GPU node.
How do 16. I get there?
The salloc command, you remember?
No, I don't remember that.
Okay, excellent. Let me find it and send it. It's in the chat.
Thank you.
How many times I copied? Okay, it's here. Let me put it again. Okay, so go to the GPU node. Okay, let me proceed where I was. Yeah. So with this command here, you pass an NumPy array and you say GPU array and you specify 2 GPU, and now this it's an array on the GPU. Okay. Now, if you want to get back the data from the GPU, so if you do 8_d.get, it will transfer implicitly the data from the device memory to an NumPy array. Okay, and this is very helpful for those that they don't want to remember all the details about copying data. Okay, now let's see an example that I have prepared here that beyond explaining this functionality of a GPU array, it allows us to use BLAS functionality. So BLAS functionality BLAS stands for Basic Linear Algebra, and and this is very useful in general for scientific applications. So you can do vector dot products, vector addition, you can do matrix multiplication. Okay, so in order to be able to use this basic linear algebra, which NVIDIA has implemented in what is called CUDA, okay, you need to either install this, which is called scikit CUDA, or use what I told you, my own Python installation, so you can have directly access. Okay, and here I import SK CUDA, from SK CUDA, I import CUDA. Okay, and this CUDA, I want to do a matrix multiplication. So I have two arrays, A and B, and I make them, yeah, it's a bit big array, not so big, but it's something decent. So I make them 10,000 times 20,000, and then they are at 20,000 times 10,000 in order to be able to do the A times B multiplication. And one thing that you need to remember here is that the ordering of the matrices, because there is the two conventions. There is a convention to put them in a column-wise way or a row-wise way. So the Fortran, the Fortran is column major, and since the blast functionality for historical reason has been implemented in Fortran, also the CUDA has this convention. And here we need to say that I need my arrays to have this Fortran notation, which is column-wise. Okay, and then after I have my NumPy arrays, I say make them a GPU array now. This is what it does here. Yeah, I put the shape of them on, I keep them here, the shape, so I remember it. And then I create the output array. So the output array, if A is MK and then B is KN, then the output is MN. And I create them to be empty because this will be overloaded, overwritten later. And then the blast functionality needs to specify an alpha and beta if you want to add to other arrays. Okay, in my case, I put beta to 0. Alpha is the prefactor of the multiplication. I set it to 1. And then the CUDA need to create, for the first time that it runs, a handle. Okay, and this handle, the first time that we call it, it gets information about the GPUs, about the system. It does some initialization, and then you can call whatever blast functionality you want. So this is done just once at the beginning, but then at the end you need to remember to close this handle. And I make here, here I call from CUDA this double precision general matrix multiplication. This is what this means. Yeah, this is the order that it needs. It needs to know the dimensions of the arrays, and you provide pointers. So if you say to this GPU arrays dot GPU data, it will return to you GPU device pointers to the data that CUDA needs in order to do the calculation. You can do timing if you want, and here, because I finished, I don't want to use CUDA anymore, I destroy this handle that I have created. Okay, and then in order to visualize this array, I say, yeah, this is in order format, in order to be able to visualize it correctly. And now I compare with the standard linear algebra implementation of Python that does matrix multiplication to see how well I'm doing when I do this calculation of the GPU. So let's run this, and then we can have a break. Okay, so when I do the multiplication, I check the difference between the CPU and the GPU calculation to make sure that it's correct. And you can see how much time it took this to be done on a CPU, the multiplication, and how much it has taken on the GPU. So the GPU is order of magnitude much faster compared to the CPU. So keep this in mind when you want to do such big matrix multiplication. Big, not small. Because if it's big, the CPU, sorry, if it's small, the CPU will be fast. GPUs are only good if the matrix it's big enough. So it should be a few thousand dimension to have a few thousand dimension. Okay. So do you have questions about this session that you want to raise now? Otherwise, we go for a break.
Yeah. I have one question, which is when I try to do also the multiplication in the CPU, it gets killed, the process. I had to comment out the lines that do the linear algebra dot product of A and B to get it to run.
What is killed, the script or the node goes down?
The script, the node, I'm still on GPU 2. Actually, it doesn't run even, yeah, well, I made a mistake. It doesn't even do even when I comment out the CPU part, still it doesn't work, it gets killed. I get the same output as you got in your screen up to the GPU multiplication using CUDA in 0.00 seconds, and then I get a kill.
We have a limitation on memory.
So let me think. Just killed without any warning or error.
Nothing, just killed.
Yeah.
Just one word, killed.
So can you do 3 minus G?
Okay. Yeah, I did it.
So what it says? How much free memory you have?
188 total, free 184, available 184, swap 0 as you.
184.
Free and available.
Yeah, you have the same memory as me. So I don't understand why it just killed it. So you didn't change anything, right? I mean,
No.
regarding sizes and...
I didn't change anything, no.
Interesting. So can you try to make it a bit smaller?
Yeah, I'll try.
I don't know if we are on the boundaries and somehow this is... because it seems like a memory issue. I don't see any other reason an app I cannot do that.
I made them an order of magnitude smaller.
Okay.
Oh, I'm just waiting now because I run it again and I'm waiting it to get killed. I don't have the prompt now.
But it should fit without the problem. It's not so big that it does not fit. It's strange.
It's 10 times smaller. I think it works.
Yeah, it works. I did it with 10 times smaller, and it works in
Okay.
seconds.
I don't know, maybe when, what I'm thinking now is when you put in this salloc that needs one GPU, maybe it implicitly using also the mem option that it may give you access to 1/4 of it. I expected that 3-G will also see it, but it seems not. However, it could be that implicitly this is implied. Because in my case, I did a salloc with 4 GPUs.
Oh, yeah, that could be a difference. Yeah, okay. Anyway,
Okay, but the idea is the same.
Yes, thank you. Yeah, that's fine. Thanks.
With that out of memory killer. Yes.
I think, Kyriakos, this actually proves your point in the fact that if the Slurm manager prompts that it runs out of memory in one of the tasks that was actually run.
Yeah, try to salloc again, but in this time put GPU 4 and then task 4. Okay, and I think you will have access to all the memory.
Okay, thanks.
Okay, so we talk again at 3. So this is that will be our last session.
Okay, thank you, Kyriakos. Thank you, everyone. Please be on time.